Hello, welcome to this video. Today I'm going to talk about Fourier series and how to use them with sounds. So the first thing I'm going to talk about is the Fourier series. So basically you will write a continuous function as a sum of sines and cosines, well, a sum of sines with varying amplitude and varying frequency. So for example, if you have a signal and you want to reproduce the square signal, so it's 1 then minus 1. So you will write it as a first sine, then you will add another sine with a different frequency, and the more you will add this sine, the more it will fit the square wave. So the goal will be to have a function, and you want to say that it's sum of series, Fourier series. So here, 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 here. I have an example. So it's sine of 3000 t for 2 seconds. So basically it's the you have a coefficient that is in front of the t, and that represents the frequency in hertz. So if you multiply by 2 pi, it will mean that the sign will cancel out, will be equal to 0 3000 times. So I'm going to compute that actually. Please, low times pi. Hello, no. Okay. Can you please compute that? No. Okay, never mind. But it doesn't matter because it will add a coefficient in front. So usually you call this omega. Well, it's not the same as the frequency actually, but it's 2 pi the frequency. Omega equal 2 pi the frequency. So you have this wave, and when you listen to it's just a sound. So if you look at the spectrum, it's just a peak and then nothing else in the frequency. So we know that the frequency is this number, and I think should be this number divided by 2 pi, because this is 2 pi times the frequency. So the frequency is this divided by 2 pi. Okay, so once we have that, we can try to build other signals. So I will try to do sine this. So we have another sine with a different frequency and with the same amplitude of the both frequency. Okay, so now it looks less than a clear signal. So here we have two frequencies, but the problem is that we have not set an amplitude. So I'm going to put 1/2 in front. Well, I'm going to put it like that. Okay. So it will mean that you have 0.5 times the frequency, this frequency, and 1 times this frequency. And you can see that the frequency, the signal is slightly different. So then you can try to do funny things with an amplitude that varies in time. So I'm going to try arctangent. Arctangent 30t. Arctangent is a continuous function. that is defined between well, here we are on 0 plus infinity, so it's 0 pi over 2. Yes, so it's always a real. It does not go to 0 nor infinity nor not defined. So it will start with a slow amplitude and then a large amplitude. Okay, so that looks like this. I think the amplitude is too large. Okay, now you can see that it starts with a low amplitude and then it converges to a biggest amplitude. Nope, still too large. How about arctangent T? Okay, so you can listen and see and notice that the amplitude is getting bigger. And then when you do the frequency, so you have a big peak, you have a big peak at the correct frequency, and then you have a little frequency that appears due to the fact that the amplitude varies in time. So it's equivalent to having lower lower signal with different frequencies. So you can also view it as a complex representation. So you know that sine is the imaginary part of an exponential. Exponential I times 30 t, oops, 3000 t. That should work. So this is equivalent to a sine, if I'm correct. Half sine. Wait, 2 sine. Yes. Yes, it's a sine. Yes, what am I saying? Okay. Okay. So we find back the sine. You can also do the thing with the real part. So it's equivalent to a cosine, and it will just have a different phase. Okay. And you can imagine doing funnier things by making it t squared. Like this. No, like this maybe. Okay. Low. Okay. So you've just listened to sine 300t squared. So it looks like this. Maybe I'm going to add another 0. Okay, so it was higher. What if I try 700 t squared? Okay, now you can see that the frequency is not very good because there are lots of parasite thingy because the frequency varies in time. So how about spectrum of square signal? Will that work? No. Square signal. I think it's called square wave. Square wave. Math function. Okay, so I, I'm I can't like really explain it correctly, but basically you have a signal that is a sum of A times sin omega 1 times t plus phi 1 plus A2 times sine omega 2 times t plus phi 2 plus A3 times sine omega 3 times t plus 3, etc. and so on. Oops, what am I saying? It's an A3 here. So basically, what you will have is uh, the first thing is we have algorithm to change a recorded input as this. We call this the fast Fourier transform, and we can determine those coefficients, and we can build signals uh, and and know the coefficient to find the best approximation for all the points we have. So so yeah, that's it. And also something I didn't mention is that if you want to have a phase, uh, well, so this was our signal from earlier. For 2 seconds, please. Okay. Now, if you want to have a phase, you need to add uh, plus I times some coefficient. So pi over 2 will make it will change the cosine to a minus sign. So it will just change the phase. Just change the phase. Okay, so you can see that it's back to a minus sign. Um, if you add something real here, so like 3, it's the same thing as putting it as time exponential 3, like this. And then it's equivalent to multiplying by exponential 3. So it will just increase the, how it's called, the amplitude of the signal. Please compute that. See, it's the same signal, but the amplitude is changed. Okay. Okay, I think that's it for this. Um, oh wait, hold on. For the square signal, I found the Fourier decomposition. So how it works is that you have a square signal, so like this, a square signal, and then you can write it as an infinite sum of this thingy. So it's sine 2 pi times the frequency times t plus 1/3 of sine 2 pi ft plus 1/5 of sine 10 pi ft. So I'm going to compute that actually. So it's 4 over pi times sine uh, sine 2 pi uh, 17 fois t yes, okay, so it's the oops, play for 2 seconds. After it's 1/3 of 6 pi. Okay. Okay. Now plus 1/3 of 1/3 of sine 2 pi times 3 times the frequency times t. Please. Didn't work. 2 times pi. Should work, no? Please. It's not hard. No. Okay, so what we know. Okay, so this is a good picture. Wait. Oh, okay, it's a GIF. So um, you have. Okay, I'm going to reload it. So you have a first the signal you want, and then you have a first sign, and then you add more and more sign to fit the square signal, and that's the whole thing of the Fourier decomposition. So that's a cool method, and yeah, that's pretty much it. So thanks for watching, and drop a like. Bye.